So we're gonna start the next talk. It's Jim from MapR. So he's replacing Michael. Michael unfortunately couldn't make it, but I think you get the as good as Michael Jim here, who's probably even better. I'm just gonna be talking about sort of Spark streaming and integration of batch and streaming.
Hi everybody, I'm Jim Scott, MapR. A little bit about me real quick. I am a co-founder of the Chicago Hadoop Users Group, big participant in the community in general. If you hear me blabber on about that at all throughout here, forgive me and accept it. So I want to start out by talking about fault tolerance. So what does this mean in a system like Hadoop? Well, in Hadoop, it was built to basically accept that hardware was going to fail. And in order to accept that, it had to solve it via software. And so when we look at a platform like Hadoop, we say, okay, we know that we've got a platform that can scale. We've built fault tolerance into the platform via the software. But what happens when you get to the development of the software you want to run on this platform? So I want to talk a little bit about developers. So we're not really talking about this kind of issue here. This is something that's being addressed elsewhere. What we really are talking about, though, is this. We need to protect against mistakes. They happen. Has anyone here ever accidentally run an update in a database that was in production mistakenly? Yeah. Kind of freaks you out a little bit. The entire intent of this talk is to literally discuss this topic. So what happened when Hadoop came along? We let the elephant in the room. We all knew it. Some things got better, some things got worse. It fixed a lot of problems, but as part of the architecture, we had to learn to accommodate other things. Everyone wanted to shoehorn everything into MapReduce. Everyone wanted to make it the hammer for all of the screws that we were dealing with. So one of the problems that exists quite heavily is when people write their software, it works great, they pass it over the wall, there's issues. So at the end of the day, what we're talking about is developers, but we're really talking about human fault tolerance. So as a system grows more complex, that we really have to have an understanding that mistakes are going to be made. It's inevitable, we have to deal with it. So when we are the people who accidentally delete things and put ourselves through this stress through a production environment, managing that, we have to kind of step back and figure out what can we do to help prevent these sleepless nights, these issues in general. We don't want to do it, we don't like it, we need to get better. So people understand fault tolerance. Not everybody quite grasps the outcome of what might happen when they do things. So we know things are going to go wrong. It happens everywhere. It can go wrong at scale with the biggest of companies that we all know about. It doesn't matter if you're a big internet company, a bank, or Google. It can happen, right? We've all seen it. We've all lived it. So this is where we get to Lambda Architecture is really here to kind of save us. Now, this concept isn't brand new, but it is what I would consider reasonably newly documented. So the concept as a whole has been around, but Nathan Mars came along and he wrote it up very succinctly. He clarified it, he gave it a name, and he made it something that pretty much anybody should be able to look at and understand. Now, for this person in particular, you know, he happened to create Storm. That alone is something pretty substantial. But the fact that he was able to take an architecture like this and clarify it for people is really phenomenal in my mind. So his experience at Backtype and when he became part of Twitter really gave way to understanding and absorbing that we have to protect against hardware failures and human errors. So when you've pushed a bad configuration file out to production, how do you recover? When we look at what is needed in an enterprise application, platform, support, operations, whatever it may be, we want to make sure we have support for both that batch and low latency. There's been too many times, too many people who have had to say, which one do I build this platform for, right? Do I want low latency? Do I want this or that? Do I want OLAP or OLTP, right? When we build relational databases, we put indexes in certain places in certain ways to support certain types of queries to make them optimized for the use case we have. It's all about the trade-offs. Well, the Lambda architecture's goal is really to remove those trade-offs. We don't want to have to do it. We've been shoehorning solutions into technologies that are there and being supported by IT staff. So why is it called the Lambda architecture? Well, data comes in one side, goes out in two other directions. So this is the Lambda architecture. So you've got data coming in, you've got it going into your batch layer, you've got it going into your speed layer. The batch layer, fundamentally, what most people should understand this to mean is really what you're creating here is a system of record. You may have heard earlier today someone say, well, you can do updates, or we're looking to try and add updates. Updates are okay, depending on your use case. But when you get into having to fix mistakes, if you allow people to update things that you use as defining your system of record, you will get into a position that you will never be able to recover from. So the architecture doesn't dictate how long you have to keep your data around. It's just that you should keep all the data, right? If you have a use case where you, by rule, by law, whatever it may be, can only keep your data around for 7 years, right? You have a time to live on your data, fine. The whole point is that you can always get back to current state by going through this batch system in the case of any type of disaster, right? Whether it be human error, whether it be system failure, whatever it may be. So when you combine the speed layer with the batch layer, suddenly you have a system that can satisfy all the queries that you have in your platform. So your trade-off between performance for OLAP or OLTP goes away. You now can support all the different needs of your business in any different way, shape, or form that you have. The serving layer, of course, is where you're going to now, if you look at it in an OLTP fashion, say, I want to build this application for my customer, and I'm going to come into the serving layer. I'm going to request my data. I'm going to get it back very quickly. It's going to combine your batch and your speed views to always give you a current look at what is real, what is now. So you've got a reliable distributed master data set in your batch layer. You get to index the data in a way to support low latency for the usage of the data. And so if you think about this use case, let's look at digital advertising as an example. A history of click events from any particular user or all users are what really derive how you want to drive the advertisements for that user. So if I go bouncing around 15 different sites that I'm tracking clicks on, I get this information. I want to be able to grab this historical data, store it, and then I want to build something that my OLTP system can actually leverage to be able to use for delivering my ad. So I want to know if you have, in fact, viewed this website before. And if you have, I may want to serve you an ad from that company because you care about their product in some way, shape, or form. So I don't want to constantly go back to all the history and recalculate that every time. I want to have a record that defines who you are. But when I want to look at a larger model, I might want to say, did you click on the ads more often when I created your record this way or this other way. And so being able to go back to that batch system and being able to rebuild a user's record on the fly, saying, I have all the historical data, I never augmented it, I can get back and create it in any way I want to. I can now use it to create more, better predictive modeling to drive a business. So what we have is all of the data that you've got in your batch view, plus the data that is streaming in. You now have this ability to say, any point in time, I want to go change my business logic. I want to do something differently. I do it at scale. I still have data streaming in on top of it. And you can do this without missing a beat in your platform at the enterprise level. If you have a bug in your code, you can fix it. If you have a bug in your streaming code, let's say you're adding something wrong. You can go back into your batch side, you can fix your bug, you can recreate it so all of your corrupted records you had are gone. It gives you a way as an enterprise to recover from failure, recover from bugs. It protects you from all of the headaches that exist. Well, ish. So if we take something that's a very simple use case for everybody to understand, flight data. Many people flew here today. This information, very easily attainable. So let's just walk through a quick example. If I have my immutable data set, I store this data in my batch layer. Over time, I'm going to add different events that have occurred, takeoffs, landings, fantastic. So what do I want to do with this? Well, over time, your data is going to grow. You're going to want to be prepared for this. You're going to need to understand what all of those different scaling factors are. But you're always going to have the ability to come in here and start asking questions and building queries that you care about. So how many planes are airborne right now? How many are airborne per airline? How many planes are currently sitting on the tarmac at every single, or at the gate of every single airport? These are simple questions, but I think my intent here really is to show you that simple questions fall into either category, right? You can have it batch, you can have it streaming. How far back do you want to look at data? What do you need to support your use cases? When you have your immutable data set, you have the ability to go in and change the rules of your world anytime you want to. So if we want to implement this architecture in our own businesses, what do we do? Well, if we start with this as the premise, we can say, I know of a lot of different technologies that would fit on this stack, and they could fall in different places. Well, here's a starter for you. Some of these components, they can meet the needs of the layers. The information in this form is not necessarily terribly helpful, but it's a good starting point for you to understand kind of what technologies are out there. So when we look at this, we can say, okay, in the batch side, Hadoop, great. I have a way to store my historical data. I want to generate queries. I want to generate views of that data. Hive, Pig, what have you. I want to support streaming. I have Kafka. Fantastic, works great. I have Storm for being able to handle my streaming. I have HBase for being able to handle my serving layer. Now some people say, well, that's a lot of technologies to have to handle for enterprise use cases. It's true. You may already have some of these in place, you may not. The nice thing is you can kind of mix and match these. This is just an architecture. This is showing you how to protect yourself from, well, yourself. So if you take it at that, you can then say, well, I could throw Spark in here, and Spark meets some of these. Maybe you have reasons why you don't want Spark in certain places, or maybe there's reasons why you want Spark in certain places and not other technologies. You may have a whole bunch of legacy code, and I say legacy very lightly because this is code that's probably only been written in the last 2 to 3 years, but you may have this now legacy code sitting in in your data center running operations, and you don't want to go through the effort to replace it. Well, these technologies all play side by side. It's one of the nice things that I see about Spark, quite frankly, is that it's rather ignorant to what else it's playing with. It just wants to play. So let it in, have fun. So when you look at these technologies in an integrated approach, there's some stuff that's already out there. Twitter released Hummingbird. There's a project called Lambda that has not quite delivered on the Lambda architecture, but is working toward that. And then Apache Spark. Well, Apache Spark really does fundamentally deliver all of the pieces necessary to satisfy the Lambda architecture. So hopefully the takeaway for most people here is you can implement the Lambda architecture pretty simply with Spark. Again, is Spark going to be every single facet of your Lambda architecture implementation? Maybe, maybe not. It doesn't dictate that it is. It just happens to have all the pieces necessary for you to support your use cases. So when we look in here, we say we can generate our views off of Spark SQL. We can support the speed layer with Spark streaming, right? We have the Spark core execution engine, which clearly can play on the batch side. But what I see for Spark that gives a lot of flexibility in this model is that you've got a data platform, right? You've got HDFS, you've got S3, you've got wherever your data is, your local file system. On top of that, you've got where are you going to execute this? You can use Mesos to manage it, you can run it in EC2, you can run it in Google Compute Engine, you can use Yarn to manage it. So you've got the core engine sitting on top of that, doing all your batch work. You've got the rest of the ecosystem there, sitting there, supporting any of your needs that you have. Now, from MapR's perspective, we actually do have a customer in Cisco who has effectively implemented Lambda architecture with Spark doing security. And it really gets to the heart of being able to leverage using a stack and the community of products and technologies that are out there to meet a need. And so they're actually doing security, threat vulnerability analysis, things of that nature, using this type of architecture. Now, again, the benefit of this technology stack, this architecture, is to save you headaches. It's to implement it a better way. There is, in this scenario right here, I believe what I've been told is they're handling somewhere around 20 terabytes a day in security threat analysis with a reasonably small cluster. So there's the site for the Spark stack, just an open source org site that basically helps catalog different use cases, implementations that are going on out there. To me, as part of the community, one of the things that I see that a lot of people get confused with is if I want to be part of the open source community, I have to commit code. It's just not true. Participating with your experience, communicating to other people, telling them what you've tried, what you've failed with. How many people here have failed with an open source technology at some point? You've had problems, you've had issues. It happens, right? You've got to deal with it. The community, this is where I see the open source community really delivering for people. Reminding people that getting out there, posting, telling people what you've done, what you've tried, helping them, someone else is going to try what you've tried. I can almost guarantee it. That is everything I have for this topic. We've got a few minutes for questions. If anyone has anything on the Lambda architecture they'd like to know. Yeah? When would you use Spark streaming versus Storm? Really, is my opinion, it's just a matter of taste and what you're doing. If you've already got Storm in place and you're happy with it and you're meeting the needs that you have, I'd probably stick with it. If you say, you know, I want to be able to leverage the same code base perhaps on the batch side and on the streaming side, with the common APIs for Spark, you have the ability to be able to use that common code base on both sides. So suddenly now, instead of having code written over here and code written over here and managing them, making sure they're in sync, it gives you the ability to simplify your stack.
Do you find that having the same code base is valuable given that you're usually using pretty different algorithms for streaming situations versus
So the question is, one more time?
Do you find that it's really helpful to have, like in the real world, like helpful to have the same sort of code base when you have pretty different algorithms for a streaming situation versus a more complicated?
Right. So is it worthwhile to have the same code running on the streaming side as the batch side when you may have very different algorithms? Well, if you have very different use cases, that's probably not really the same code base. If you're looking at it from a OLTP type of perspective, where you're trying to deliver something to an end user, you're probably going to have the data be the same in both, or the algorithms be the same in both places. One's taking a larger batch perspective to be a catch-up model, whereas the streaming is doing some type of incremental windowing and adding to what that view is. Anybody else have any questions? Yeah.
In the Lambda architecture, do you go through all your data or your fact space with batch all the time, or you just split it over in pieces? You have an intake of terabytes per day that you're going to.
The purpose of the batch model is literally to go back and recreate. So you always want to go back through everything. You don't want to go through an incremental model in the batch side. The reason is you're protecting yourself from mistakes, right? If you put a bug into your code unwittingly, this gives you the ability to come back from it. So if in your model you say, I have a terabyte of data coming in every day, and I'm handling that on the streaming side. Well, you may not need to run your batch constantly every day, right? You may choose to, but you don't necessarily have to. So at a minimum, the batch side is there to protect you and save you from yourself and or others, whoever's mean, malicious, and all that good stuff.
It's not time to run your batch growing incrementally with the size of the data.
It depends on your algorithm, I think, right? It depends on what you're doing with your data. If you're literally taking as part of your batch process, say, I care about every record forever for every user, then yeah, you're always going to say, however many records I have, I'm going to process all of those. But if what your output is, the views that you're generating from your batch side, are literally cases where you say, I want to recompute the previous 10 days because maybe in your use case for those views, you only care about those 10 days. Maybe you had it in your algorithm or you wanted to reproduce your records from that point in time. It gives you the ability to have the flexibility to meet your needs. Yeah.
So I have a library that comes in doing the batch process, like to certain things. So the same algorithm is still being used, one algorithm is still being used to process the stream data on the library. How do I guarantee that after I redo the batch processing, how do I go back to the last chunk of data that came in streaming process?
Well, on the streaming side, your data is always going to be coming in. You're going to be dealing with windows of data as they come through. On your batch side, as you're persisting all of this data to process it, you're going to take that entire batch of information. So there's not really any where do you pick up on the streaming side, right? Your stream is going to always be picking up windows that you've defined in those increments to deal with that data. So for you to be out of sync would literally be you having the wrong code on the other side.
So what if my streaming data, my calculation cuts out my historical data, like what application on top of it?
What if your streaming data depends on your historical?
My historical data used by the last batch of wrong.
Well, again, this gives you the ability to go back in. If your batch data was wrong, you go rerun your batch. Your batch will never include the stream data. Your batch will include the batch data. It'll regenerate your output and your views, and you can use that to restart your streaming side if that's how you decide to do it. Yeah. Well, logistically speaking, right, so logistically speaking, how do you handle if you create a new batch output and you want your streaming side to pick it up and drop what it had? The architecture doesn't really dictate how to do it, but you could do it as a listener, right? You could have it periodically go check and see if there's a new a new update that you need to dump all your streaming context for and pull it back in. I don't know of any specific best practice that says do it this way or that way. Yeah.
So in that in the example that you had, the airline data,
Yep.
if we have to do like the last top 10 busiest airport of the last 2 weeks, right? And if you have to show that in real time, what kind of
Well, if you're going to be looking at a top N from real time, you're going to want to be generating the data from the streaming side, right? So whatever information you had in your batch side being generated, you've got your time differential happening in the streaming side. So your serving layer is going to combine the data coming out of the batch side and out of the streaming side into what your final output is. So if you don't run a batch in the last however many hours or days, what's coming out of your speed layer is going to be delivering you effectively all of your results, but that's going to get combined for you in the architecture to be what you serve.
Jim, maybe just take the rest of the question offline.
Okay.
We love you on the stage, but
where would you combine that though? Where would you combine that though, your batch and the stream?
Well, it's part of the serving layer to combine those. So you've got the batch, you've got the speed, and you've got the